an example. Okay, so this is an example I'm going to do for you. Okay, as opposed to being something that you do yourself. Okay, and it's basically we've got a locomotive car, so not a car, but a locomotive on rails. The mass of 2 tons, travelling at a velocity of 10 metres per second. It's stopped at the end of the tracks by a spring damper system. Okay, so it's got those buffers at the end of the end, where you've got a platform, and the train is pulling into the platform. And obviously if it overran, it would hit the buffers. Okay, the stiffness of the spring is 40 newtons per millimetre. Okay, and the damping constant is 15 newton seconds per millimetre. Find the equation x of t representing the motion of the locomotive when it hits the buffer. Okay, so there's my information. So I'm going to just go to the next one. There's the same question in a bit smaller fashion. There's a few steps we've got to solve this. Okay, the first thing we need to work out is what's zeta damping ratio. So I know it's going to be c over 2 root mk. So my damping constant is 40 times 10 to the 3. Notice that because it's millimetres, no, that's not 40, it's 15, okay? So, because we've got newtons per millimetre, that's equivalent to kilonewtons per metre, okay? So I've got the 10 to the 3 in there. Over 2 root m, which is 2000, k is 40 times 10 to the 3, okay? And so if I do that sum, 15 A3 divided by 2, you've got 2000 40 A3 0.8385. This is my damping constant. Three. Okay, so that's the first thing I need to work out. This is the equation I need to find is x of t equals a e to the minus zeta omega naught t omega dt plus alpha. Okay, so the next step of the equation is to work out what omega d is, or omega naught. Okay, is root k upon m, so that's 40 times 10 to the 3 over 2000. So that is going to be 40 E3, 2 E3. Radians per second. Omega d is omega naught root 1 minus zeta squared. Okay, so I've got that. If I swap them around, 1 swap, square that, subtract that from there, square root that, and multiply by that. Okay, 2.437. Okay. Okay, so that's for my omega d. So we've got everything. We've got zeta, omega naught, omega d. So I could start writing it out. Okay, x of t is a e to the minus 0.85 8385 times by 4.4721 t. Okay, cosine of 2.4367 t plus alpha. Okay. So there's my basic equation, but there are two unknowns, a and alpha. Okay. These things, here we don't know. We need to find these from initial conditions. Find from initial conditions. Which are, what are they?
When t is equal to 0.
When t is 0. So the displacement and the velocity when t is 0. Okay. What have we got? The train's coming along and hits the buffer mass spring damper system. Okay. What's the speed at which it hits there?
10 meters per second.
And what's the position when it hits? Okay. It's 0. So obviously the thing's coming along. The moment that we're interested in is the point of impact. At the point of impact, the damper hasn't moved, or the spring damper hasn't moved. Okay. So the position's 0, but obviously we know that the point of impact is going to be moving at 10 meters per second. Okay. So that's the initial conditions. Okay. So there are a couple of initial conditions. Okay. Been defined in the system. I'm going to go to the next slide. Or are you still writing?
No, you.
It's just more space. Okay. So I've got my initial conditions. X of 0 is 0. X dot of 0 is 10. Okay. Meters per second. So there's my initial conditions. And so my equation, obviously, I'm just going to write it in terms of variables because it makes life a bit easier. Okay, there's my first equation. So x of 0, we know that equals 0, okay? I've got a, e to the 0 is 1, so we forget about that. We've got cosine, omega dt is 0, so we've just got cosine of that. Now, for that equation to be true, okay, for that equation to hold true, either a needs to be 0, or cosine alpha needs to be 0. Okay, can a be 0?
And no.
No. If a is 0, there's no oscillation. This thing's going to oscillate. So cosine alpha must therefore be 0. So, I think it's cosine alpha. What's the inverse cosine of 0? What does alpha need to be for it to be 0? Yeah. So alpha's pi over 2. Okay, now, the other equation, I need to find the derivative of that equation. I've given it in the question, but let's do it. Okay? If I've got my equation here, so I'm going to, let's copy this. Start with A. Come on. There's my equation, okay. If I let's go for a different colour. If I say this is U, this is V, okay, we know the product rule, okay, so I'm going to say x dot, we've got A times U times by V, okay, the product rule, x dot is A. Remember this? U dv by dt plus v du by dt. Yeah? Remember the product rule? from engineering maths. Okay, so that's obviously what we've got to do. So if I say U is that and V is that, so I've got A, U dV, so I'm going to go for, well, in fact I'm going to do V du first. I've got minus zeta omega naught, e to the minus zeta, oops, omega, zeta, cosine of omega d g plus alpha. Okay, and then I've got plus V du, so I've got e to the minus zeta omega naught t times by minus omega d sine of omega d t plus alpha. Okay, now I'm going to simplify that out, so I've got a e to the minus zeta omega naught t minus zeta omega naught cosine omega dt plus alpha minus omega d sine. Okay, so that's my derivative. Let's get rid of all this stuff down here. So x dot 0 is going to be a, e to the 0 is 1. I've got minus zeta omega naught cosine of alpha minus omega d sine. And this we know equals 2. Yeah. What's cosine of alpha? It's just there, look. 0. Sine of pi by 2 equal to 1. Okay. And so this equation reduces down to a times by minus omega d. So therefore a is 2 divided by minus omega d. You've got 2 divided by 2.4367. 2.4367 minus. So if we do the sum, this comes out to be minus 4.104.
Where did the 2 come from?
There's the, sorry, it's not 2, it's 10.
Yeah, okay, yeah.
So let's check that. So was the omega d minus, and then we've got 10. Swap. 4.1039 is what I'm going to find. Okay. And so my oscillation, x of t, minus 4.1039 e. So what's we've got point. What have we got? We've got the damping ratio. That's the frequency. So that's this 0.8385 times by 4.47. 3.75, or 3.75 e to the minus 3.75 t cosine of 2.4367 t plus. There. Is the solution. Okay. So, like I said, this is all being recorded, okay, and these solutions will be on Blackboard as well, okay, for you to fill in the blanks in your notes. Like I said, if you actually print out your notes, you know that printing is free for you. Black and white printing is free for you. Okay, you can obviously come in here with the notes printed out if you would like to, and fill in the gaps as you can. Okay. So, like I said, all that's up there. I'll just come back to the first slide, about the learning objectives. You should be able to be familiar with the forms and solutions for both free and forced, undamped and damped single degree freezing systems. Okay, so we've done free, okay, for both undamped and damped. Next week we'll do forced and damped. Okay, so we've done 3 out of 4. Okay, identify the correct form of solution depending on the problem being posed and find equations. Well, we've looked at a few problems where we had a mass spring system and a mass spring damper system. So we've done a bit of that as well. Understand how for all systems amplitude ratio varies with different driving frequencies. Okay, so like I said, we looked at that a little bit in the case of the undamped system. We'll do them for the damped next week and be able to convert solutions. That's next week. Okay, so there we go. So thank you very much. I shall see you all on Monday for the tutorial sessions for this module. Okay, where we're going to probably do another problem similar to the example there. Okay, and we can look in a bit more detail.